The goal for today is to talk about piecewise functions. And how do we do the Laplace transform of piecewise functions? Now, the good news is there is a way to do it, and actually Laplace transforms are really good at handling piecewise functions, particularly when they're involved in differential equations. We'll talk more about that next time, but now we want to learn, well, how do we handle that? And it comes down to the following example. So we want to find the Laplace transform ut minus a f t minus a. Now we've talked about the function ut minus a before. Now u is the unit step function. We should really think of it as an on-off function. And so what happens here when we look at u of t minus a, it says we're going to have two things. This is either going to be 0 if we're below a, and we're going to be 1 if we're greater than or equal to a. So in other words, up until the point a, everything is 0. And then all of a sudden, something happens. Now, what's happening? Well, what's happening is the f t minus a. Now, what is that? Well, it's simply f, but now we've shifted it over. So we've shifted f over by a. Now visually, let's talk about what's going on. So we have our function f, and so what's happening with f? Well, let me grab a good color here, is we're starting at time 0, and we have some type of behavior. Okay, so this is our f of t. Now, what we do is when we graph u of t minus a, f of t minus a, well, we identify a, and what's going to happen? Well, we're going to be 0 up to a. So we're 0, and then we jump up, and we follow the same behavior. So in other words, these are the same, it's just shifted over. So this is u of t minus a, f of t minus a. So that's the whole thing, right? All we've done is move it and shift it over. And you might say, well, wait, that's not the same thing as shifting all of f, right? Because we don't take what's below. Well, we don't, because when we talk about Laplace transforms, we don't care what came before 0. And so really for all Laplace transforms, you might say it's always 0 below 0. So we're shifting it over. Okay, now that helps us understand what we're doing. We still have to do it, and so let's get into it. Well, what do we do? When we have something that we haven't done before, usually we say, do we have a rule, or do we make a rule? This is the latter. We're going to make a rule. So we're going through our process. We want to find the Laplace transform u t minus a, f t minus a, and we say, all right, by definition, this is the integral 0 to infinity e to the minus st times, well, u of t minus a, f of t minus a, and then dt, right? Because whatever it is that you plug into the Laplace transform, in other words, this expression, you just put it into the integral. All right, now we say, okay, let's take advantage of our unit step function, right? Our on-off switch. We say, look, we're off until we hit a, and then we're on. So we say, okay, what we can do is instead of going 0 to infinity, we can go a to infinity. All right, so first thing is we say, look, this is the integral a to infinity. And now we can say, in there, we're on. So we can drop our u of t minus a. All right, great, good. Now, the next thing is we'd say, look, we'd really like to have the inside not have that minus a, because we kind of want it to look like f of t. And so we say, well, we could do that if we make the right kind of change, the right kind of substitution. So let's talk about what kind of substitution we want to make. So we're going to take our t minus a, and we'll call that a new variable. We'll give it a t sounding variable, tau. It's sort of like Greek for t. So tau is t minus a. All right, now it's not too hard to see. D tau is dt. That's good. Our bounds will be easy. A minus a is 0, and infinity minus a is still infinity, right? Infinity is very resilient. You can subtract off a lot and still be really big. All right, so that really just leaves us with this one place. And, well, for that, we'll say, look, we can solve for t. So t is tau plus a. All right, so we have our substitution. Let's go ahead and carry that substitution out, and let's see what we have. So we've already talked, our bounds are going from, now, these are our t bounds, remember. We're going to tau bounds, 0 to infinity. All right, and now we have e to the minus s tau plus a, because we're replacing t by tau plus a, f of tau d tau. Well, we're almost there. We can distribute through, and we can say, well, this is really 0 to infinity, e to the minus s tau, e to the minus, I'll write as a times s, and f of tau d tau. Now, as we look at this, we say it's getting really close to a Laplace transform. Let's just note that this part, there is no tau. So in respect to the integral, it's a constant, so we can move it out front. All right, well, so we now have that this is e to the minus a times s, right? We pulled it out front. Integral 0 to infinity, e to the minus s tau, f of tau d tau. And our great aha, we recognize this. We've seen this before. This looks a lot like a Laplace transform, because it is. It's a Laplace transform of f. And so we say, lo and behold, this is e to the minus as, a Laplace transform of f of t. All right. So there we go. And so, okay, maybe we'll put, instead of following it all the way through, let's just put them right next to each other and say, what do we see? Well, we see the following. Laplace transform f of t, and there's an e to the minus as. And so the punchline here is when we see this shift over, well, we say that adds an exponent, and then you do it as if there were no shift. And that's it. That's the whole thing. Right? Good, good. So here we have our formula. The Laplace transform ut minus a, ft minus a is f of s, and remember that's just the Laplace transform of f of t, e to the minus as. Now, again, think about the pieces. And so what do we see? Well, when we see a u of t minus a, well, that tells us that's going to be attached to an e to the minus as. So as soon as we see u of t minus a, we're like, okay, in the Laplace transform, we're going to have an e to the minus as. Now the question is, what's attached? Well, to do that, you say, all right, look at the function, right, next to it, f of t minus a, and now do it without the shift, and say, okay, remove the shift. What does it look like? Take the Laplace transform of that, and that gives you your f of s. So f of s is without the shift. So f of t without the shift. And now, what's the key? So whenever we're applying this rule, the most important thing is that what we have right here is in terms of t minus a. If it's not in terms of t minus a, we can't use the formula. And so we say, oh, so we got to just make sure it's in terms of t minus a. So how do we do that? Well, pro tip, right? this is for the professionals. F of t is f t minus a plus a. So if it's not in terms of t minus a yet, that's the work. That's the work that you need to do. Make sure you put it there, and that way you'll get the right answer. Now, remember, every rule for Laplace transforms is also a rule for inverse Laplace transforms. And so you can imagine taking the inverse Laplace of both sides. So this says if you have the inverse Laplace of something e to the minus as, you say, aha, as soon as I'm seeing an inverse Laplace and I see this e to the minus as here, I know that's going to involve an on-off switch. It's a shift over by a. So I know that there's something happening at a. And then we say, all right, after we've done that, we say, all right, to figure out what's attached, take the inverse Laplace of this part, and then don't forget to shift it. So you have to make sure to shift. It's not just enough to take the inverse Laplace. So if it's like t, it becomes t minus a. If it's sine of 2t, sine of 2 times t minus a, and so forth and so on. And so just remember that. And as it says, it's useful to write down the effect from each part. So what does that mean? It says, think about what happens. If you have things multiplying, you see this e to the minus as, all right, I know there's a u of t minus a and a shift by a. This f of s, all right, I know what f of t is, and so that's going to become f of t minus a. Understand how things fit together. Once you understand how things fit together, then you just say, what are my pieces? And they'll mesh, and it'll be beautiful. Now, I like to look at these rules here and think back. There was another rule, one of our first rules we talked about, and that was that the Laplace transform, when we had an exponential e to the ct f of t, do you remember what that was? That became f of s minus c. So, in other words, when you had an exponential in the front, that led to a shift. And so I think it's really beautiful that we see that, lo and behold, when we have a shift, it leads to an exponential. And so there's this beautiful symmetry that goes on. And I really, the more you look at it, you start to see patterns. Patterns are beautiful, and they can help you remember things. But of course, there's the details. And so that's why don't be a hero. Use your table. Learn to use it. After time, you'll know your table so well, you won't have to use your table. But for now, use it. Use it. All right, good. Now, I mentioned we're talking about piecewise functions, and the reason we bring it up with the unit step functions is that unit step functions are great for piecewise functions. And it's that on-off behavior. And so what you say is, well, suppose I have something which changes behavior at several points. Well, if it changes behavior at a certain point, I say, well, what's the behavior that came before versus what came after? I want to turn off the before. I want to turn on the after. The way that you do this is you take your unit step function, you subtract what came before. So that's why this is a turn off the before, add what comes in after, turn on the after. And when we're talking about before and after, we mean right at that defining point. We don't care what happens like way down, far away. What's happening right there. And so, in particular, all our piecewise functions, in order to plug into the machine, we're going to rewrite in terms of our u of t minus a, and more particularly, things that look like u of t minus a, f of t minus a. And so that's why we need these rules, because now we're ready. Now we can start doing examples. Practice, that's it. We need more practice. So let's get into it. So let's start slowly. Well, we have a couple of examples. We want to find the Laplace transform e to the 2 minus t, u t minus 2. and the Laplace transform cosine of 2t u t minus pi. Okay, so now we remember our rule, and so we can write it down. So we're ready, and that tells us that the Laplace transform of f t minus a u of t minus a, doesn't matter which one goes first, is equal to e to the minus as f of s. All right, so let's do these one at a time. Okay, so we'll start with the first one. So here we go, we'll call that a. Now what do we see here? Well, before we do the Laplace transform, we're going to talk about our pieces. And this part right here is very easy to cue off of. We say, all right, we see t minus 2. So this says that our t minus a is the t minus 2. So that's what we're looking for. Now that says what's attached to it, we want to make sure is in terms of t minus 2. Now, right now, what does it say? It says 2 minus t. So we say, okay, how do we make a 2 minus t look like a t minus 2? Well, that's not so bad. What we can do is we can pull a negative out. So e to the minus t minus 2 u of t minus 2. And now we have the right format. F t minus a u t minus a. All right. So for this, what we can now say is that the Laplace transform of our function, it's the same function, just written in a different way. A lot of what's going to happen today is rewriting. So that's our practice. Learn to rewrite. Because we see our shift says we're going to get an e minus 2s, right? So that's, when we see this unit step function, we say, okay, there's going to be an exponential function. Now, for this part right here, what are we going to do? Well, we're going to be careful, and we say, well, when we're thinking about how to do the transform, we don't think of f of t minus a. We say, well, what would be f of t? So here, this is f of t minus a, where f of t is e to the minus t. So I say, okay, t minus a becomes t. And now, well, what's the Laplace transform of e to the minus t? Well, it's 1 over s minus 1. So that's going to be what happens here. And so, putting them together, what do we end up with? Well, we end up with e to the minus 2s over s plus 1. All right? There we go. Great. So, that's the process. Okay, you know, this isn't looking so scary. Well, let's keep going then. Now, what's our next one? Well, we'll call it B. All right, so here we go for B. Again, before we start Laplace transform, let's think about rewriting. So we have cosine 2t u t minus pi. Now, again, we're looking for the u function. That's our t minus a. So we know, we say, okay, we want to rewrite this piece in terms of t minus pi. Well, it's not there yet. So what are we going to do? We're going to get it there. All right, well, how do we do it? Well, if we don't see it right away, well, we always have our classic add, subtract. So we say, look, t is the same as t minus pi plus pi. All right, and look at how many parentheses are. That's so many parentheses. We're definitely not losing any points. There's so many parentheses there. So just be careful here. And if you multiply this through, this is cosine of 2 times t minus pi plus 2 pi. All right, well, that's all well and good, but how do we handle this plus 2 pi inside of a cosine? Well, we start thinking about the cosine function. What do we know about cosine? It likes to hang out with sine because it's cosine, right? No, that's not what I'm talking about. it has lots of properties. One of them is that it's periodic. It repeats every 2 pi. Ah, so if we take this function and were to cover it, it's the same function, right? Because this is a shift over. So we're like, okay, great. So this is the same as cosine of 2t minus pi u of t minus pi. Okay, now we're ready. So here, we're not ready to apply the rules. But here we are, because we've rewritten it in terms of t minus a. Well, okay, so what do we have? Well, we now use this form. So the Laplace transform, cosine of 2t minus pi times u t minus pi will be, well, we see the u of t minus pi. We say, okay, as soon as I see that unit step function, I know that on the other side, we're going to get e to the minus pi s. Right? We are. Okay, so this t minus a, we have e minus as, so minus pi s. Now the question here is, what about this other part? Well, so this part, again, that's our f of t minus a. And we say, all right, well, what is f of t? F of t would be just the cosine of 2t. We say, ah, okay, we know how to handle that. So cosine 2t, there's a rule. What's our rule? So for cosine, it's going to be s squared plus b squared. I'll write that as 4. Excuse me. And then on the top is s. All right. And, well, okay, which becomes, we'll put it right here, multiplying these together, s e to the minus pi s over s squared plus 4. And there's our answer. All right, good. Well, good warm-ups. Let's look at some more problems. So let's find the Laplace transform t squared u t minus 1 u 3 minus t. Well, let's start by thinking, what's this here? We have multiple on-off switches multiplying together. And you can almost think of this in terms of logic, if you like a logic puzzle. You say, well, in order for the whole thing to be on, they both have to be on. Now, we say, look, for the first term to be on, we need to be above 1. So we need t minus 1 to be positive. For the second one to be on, we need to be below 3, because we need 3 minus t to be positive. And so we could say, oh, the net effect of this is that we're going to turn on at 1 and then turn off again at 3. And so, okay, all right. So here we have a turn on at t equals 1. And the reason we turn off is because it's 3 minus t. And so it's on up until 3. So this turns off at t equals 3. So what does this tell us? Well, it tells us our function has the following. We say there's time 1, here's time 3, and initially it's off. So from 0 to 1, we're off. And then we jump to the on position. And we follow t squared up until 3. And then at 3, we're back off. Okay, so there we go. That's our function that we're trying to take the Laplace transform. It's a visual way to represent it. So what do we need to do? Well, we can't have multiple u's here. We have to get it into the form ut minus a, ft minus a. We are allowed to have multiple pieces, right? That's okay. Multiple pieces, no problem. But we can't have multiple u's. And so we say, okay, well, let's just think about our function. And so our goal here is to write the function. Well, we have our t squared u t minus 1 u 3 minus t is, well, if we think about it in terms of the normal way we write a piecewise function, we say it's 0 if t is less than 1. It's t squared if 1 is less than t less than 3. And by the way, don't spread too much about, wait, which one is 1? Is 1 0 or 1? Single point won't matter for today. All right, but anyways, 0 if we're above 3. All right, but again, that's not what you can plug in. You can't plug this into the Laplace. You can't plug that into the Laplace. You can't plug a picture into a Laplace. You got to keep going until you have something you can plug into the Laplace. So now we just start saying our behavior. What's our initial behavior? Well, it's initially 0, right? Because that's how we start. When do we change? At 1. Okay, so then we're going to have a change at 1. So we put in u t minus 1. What's our change? Well, we say what came after versus what came before. So what comes after 1 is the t squared. We're turning that on. And then we're subtracting what came before, which is 0. Now, we're going to say, what is our next change? 3. So, u t minus 3. And then we say, all right, what's our after? 0. What's our before? T squared. And there we have our function in one line. All right, good. Or if you like, here we have, this is our u of t minus 1 times t squared plus u of t minus 3 times t squared. Oh, sorry, not plus, minus, because of the minus. All right. Are we ready to feed this into the Laplace transform? No. Okay. All right, so what do we need to do? Well, the thing is, we have our u of t minus a. This needs to look like t minus a. And right now it doesn't. It looks like t. So how do we change it? Well, we do similar to what we just did. We say, okay, so our function, and let's actually give a name to this. So we're going to call this our f of t. So this is our function. So here is f of t. And again, this is also f of t. And so we can say, all right, well, look, f of t is equal to, there's the u of t minus 1. And then for t squared, we'll think of this as t minus 1 plus 1 squared. And now we'll do the same thing, subtract u t minus 3. And here, t minus a is t minus 3. So we're going to have t minus 3 plus 3 squared. Okay? Now, are we ready? No. We have to expand. All right. Well, here we go. So this would be u of t minus 1 times, well, we'd have t minus 1 squared plus 2 t minus 1 plus 1. Okay? Subtract u t minus 3 times t minus 3 squared plus 6 t minus 3 plus 9. Now are we ready? Yeah, we are. Actually, we're good, right? We've got our u of t minus a, f of t minus a, and there's another u of t minus a, and again, f t minus a. So we're ready to go. Okay, good, good. Well, we've worked hard. We should at some point actually get to do a Laplace transform on this problem. So we're going to take the Laplace transform of u t minus 1 times our t minus 1 squared plus 2 t minus 1 plus 1, subtract u t minus 3 squared plus 6 t minus 3 plus 9. All right, so here we go. piece by piece. No need to rush. Take your time. You should always savor the moment, right? Like, a fine problem we have here. We see u of t minus 1. Okay, that tells us we're going to have an exponential on the other side. So this is going to become our e to the minus 1s. So e to the minus s. Okay, now this is our f of t minus 1. So, what do we do? Well, what would there be if there weren't t minus 1s? This looks like, we'll put in quotes here, t squared plus 2t plus 1. So what we're going to do is we're going to apply the Laplace transform to this expression. Say, okay, so e to the minus s, the Laplace transform of t squared, well, that's going to be 2 factorial over s to the 2 plus 1, plus 2 times Laplace transform of t is 1 factorial over s to the 1 plus 1, and Laplace transform of 1 is 1 over s. Okay, that's the first term. Now, we get to do that whole thing again. So, we see u of t minus 3. That tells us, of course, we're going to have an exponential, e to the minus 3s. And we'll do the same thing that we just did. So, namely, we're going to look at this and say, this is our t minus a. What if it was just t? Well, it would be t squared plus 6t plus 9. And that's the function that we're going to think of taking the Laplace transform of when we attach it here. So, all right, so that would be, what do we have? Well, t squared, 2 factorial over s to the 2 plus 1, plus 6t, 1 factorial over s to the 1 plus 1, plus 9, and 1 over s. And we're essentially done. I'm just going to go ahead and just clean up these numbers. E to the minus s, we have 2 over s cubed plus 2 over s squared plus 1 over s, minus e to the minus 3s, 2 over s cubed plus 6 over s squared plus 9 over s. And there we are. You'll notice that's actually probably a little bit longer than you thought. You said, oh, t squared, how hard could that be? Well, because you got to get that into your t minus a, it can grow. So these problems have a tendency to grow on you. But that's not the worst thing. All right, well, let's keep doing more practice. Find the Laplace transform of the function shown in the picture below. Okay, so now they've given us a function in terms of a picture. All right, so the problem is you can't feed a picture into a Laplace transform. So what we have to do is say, okay, we've got to rewrite it to something that can. Now, here we see there are 3 behaviors. There's this going up, there's this going down, and there's this staying level. So let's rewrite it as a more typical piecewise function. We say, okay, there's 3 things happening here. There's something happening between 0 and 1. There's something happening between 1 and 2. And there's something happening if we're above 2. Now, above 2 is pretty easy to spot, so we'll go ahead and throw that in at the start. Now, from 0 to 1, it's a straight line. We're starting here at the origin. So once we know the slope, that's everything we need. Well, we go over 1, up 4. That's a slope of 4. So this is 4t. All right. How about 1 to 2? Well, now we're going down. So it's down 4 over 1. So that's a slope of negative 4. Okay, slope is negative 4, so it's minus 4t. But then it's minus 4t plus something. Now the question is, what? Well, we can do a couple things. We could visualize and say, okay, if we kept this going, where would it intersect? Well, it's not too hard to imagine. I went over 1, up 4. So I'd go over 1, up 4 again. So the intersect would be at 8. Another thing you could do is say, well, look, when I plug in 2, I have to get 0. So I'd have to have negative 8 plus something is 0. Oh, negative 8 plus 8 is 0. Okay. So that's our function. Now instead of a picture, in a more typical piecewise thing, we're not ready yet. We've got to rewrite it in terms of our u's, all right, our behaviors. So we say, okay, we start at the beginning. It's a very good place to start. And we say, all right, initially it's 4t. So that's our first behavior. Where's our first change? Our first change is at 1. Okay, so we have a u of t minus 1. And now we say, all right, what's happening after that? Well, after 1 is this minus 4t plus 8. So we're going to turn on the minus 4t plus 8. Subtract, what was it before 1? It's the 4t. Okay? So before, subtract, sorry, after, subtract, before. Yes? Turn on, after, turn off, before. And now there's one more place where it changes behavior. So that's u of t minus 2. And what do we have? Our after is now 0. Subtract our before. That's minus 4t plus 8. Okay. All right. Let's keep cleaning it up. So we've written in one-line form. We're not ready for Laplace transforms just yet. This is 4t. Now here we can combine. We have minus 4t plus 8 minus 4t. So that's minus 8t plus 8. And then here, well, we'll just write this as u of t minus 2 times 4t minus 8. Now we have our mindset, which is to say, I want what's multiplying this u of t minus 1 to look like a function in terms of t minus 1. And what's multiplying this u of t minus 2, I want that to be a function in terms of t minus 2. So we stare at this and say, how close are we? And then we have our grade. We're really close. We're really, really close. Because what can we do here? Well, what we can do is pull out a negative 8, and then we have a t minus 1. And we're like, t minus 1? That's awesome! And we come over here and say, well, what can we do? We could pull out a 4. What do we have left? T minus 2. Double awesomes! Wow! We're doubly awesome! That's so cool. All right, so what do we have? We have 4t plus, well, actually, let's not put a plus. We'll change this to a minus 8 u t minus 1 times t minus 1. And here will be a plus 4, and then u t minus 2 t minus 2. Okay, good, good. Now, we're ready. It's of the right form. Okay, so everything we've done so far has all been about saying, what's another way to think about this function? We started as a picture. We went to piecewise. We put it in terms of u, and then we made sure it was of the, u t minus a, function t minus a variety. So in other words, it's all been laying the groundwork. Now we're ready to carry out the actual computation. So here we go. Here we go. We have that our Laplace transform, and it's the Laplace transform of our 4t minus 8 u t minus 1 times t minus 1 plus 4 times u t minus 2 t minus 2. Okay? I'm just going to go through term by term. Now, the first thing, well, there's no u. Well, that's good. So what do we have? Well, it's 4, and then the Laplace transform of t is 1 over s squared. Then we get the minus 8, and we say, okay, we see a u of t minus 1, so that tells us that we're going to get an exponential. So that gets us the e minus s. And then this part right here, we say, well, think of it as if it's just t, right? We rewrite it instead of t minus a as t. And we say, well, what's the transform of that? And that's 1 over s squared. Oh, that's not so bad. Plus 4, and okay, we see again unit step function. So we know we're going to get e to the minus 2s, and then this t minus 2, again, we do the same thing. Hey, this is really like t. And so that's a 1 over s squared. I don't know why I changed colors there, but that's all right. Sometimes that happens, right? Color happens to everybody. Now that's the answer. We can maybe do something and say, hey, since all the terms have a 1 over s squared, might as well pull it out. So we have a 1 over s squared, and then what do we have? We have 4, and then minus 8 e to the minus s, and then we have a plus 4 e to the minus 2s, and there we go. See? It's not so bad. It's doable insofar as we can do it. Not that I can do it. You can do it too. We can do it. You can do it. I believe in you. Do it! Do it! Since we've now had practice with Laplace, let's also do inverse Laplace, because it goes both ways. Okay, so we have some simple warm-ups. Well, simple, let's be careful what we call simple. And we want to just practice doing the inverse Laplace of a few things. So let's start with this first one. Now, as soon as we see an exponential function involved, we know that means there's an on-off switch, a unit step function, a shift has occurred. So what do we do? Well, I like to think about this as two parts. So I'm going to rewrite this. This is the inverse Laplace. We have the e to the minus 3s, and then the 1 over s cubed. All right. Now, for the time being, let's set this aside. Well, we won't worry about it. 1 over s cubed. What do we do? What do we do? Well, how do we take the inverse Laplace to 1 over s cubed? It's very close to one of our rules. Now, one of our rules says, and well, we always have time for a rule, right? We'll write our rule somewhere. Okay, down here. So we have that the Laplace of t to the n is n factorial over s to the n plus 1. Okay, so we'll have some space to do some scratch work. So it looks a lot like that, because we have s to the 2 plus 1. What do we want upstairs? We want 2 factorial. So we want a 2 upstairs. So we say, cool, let's put 1. You know, it's one of the great things. Like, if you want a 2, go ahead and put a 2, but then how do you compensate for that? Okay, so we'll put a 2 upstairs. And how do we compensate? We'll put a half out in front. All right, so now we're ready, because we can take our pieces and put it all together. So the e to the minus 3s, that tells us, hey, we've got our on-off, and we look up here at what's upstairs, and we say we're doing our on-off at 3. So u t minus 3. Now, 2 over s cubed. By itself, we'd say, okay, according to the rule, this is t squared. However, because of the shift it's attached to, we say, all right, what will happen is it won't be t squared, it will be t minus 3 squared, right? So just take the function and carry out the right shift. So everywhere you see t, put t minus 3. And that's it. We're done. And you're probably thinking, wait, what? Shouldn't it be longer? No, no, no. Sometimes problems can be quick. This is just helping us practice. Okay, let's do more. Well, what do we have here? Well, again, let's pull out the exponential part. So we have inverse Laplace, e minus pi s, and 1 over s squared, and 4 we'll write as 2 squared. All right, now, does that look like something? Well, when we look at our table, it does look like something on our table. Namely, if you look through your collection of rules, one of your rules looks like sine of bt. And what is that? Well, that's going to become b over s squared plus b squared. You say, perfect, if we only had a 2 upstairs. You know where this is going. If you want a 2 upstairs, you put a 2 upstairs. But make sure you find a way to balance it. And how do we balance it? Put a half. All right, now we're ready. So, what do we have? Well, we don't forget the half that we introduced. We have this e minus pi s. Say, okay, that's great. That tells us the shift. We have our on-off, and we go by what's upstairs, minus pi. Yeah, it can be weird numbers. It doesn't have to be whole numbers. No problem. Now, this other part, well, what's going on here? This part, well, that looks like sine of 2t, right? I'm just applying the rule. So we say, okay, great. That's sine of 2, parenthesis, t minus pi. Okay, good. Now, are we done? Absolutely. Can we go further? Why not? What can we do? Well, one thing we can do is say, well, notice if you distributed that 2 through, so 2t minus 2 pi, what do you see? Well, this part right here is the same as sine 2t minus 2 pi, but sine repeats itself for every 2 pi. And so, this is the same as sine of 2t. So we could have also written this is also equal to 1/2 u of t minus pi times sine of 2t. Both would be fine. But just to show you what we can do. All right, well, these are funner. At least they feel funner. All right, now what about here? How do we handle this? Well, we're going to take advantage of our minus sign upstairs. Notice that we really have 2 different shifts going on. What are our shifts? Here, we're going to have a shift by 1. Here, we're going to have a shift by 2. Because we're going, what's attached to that? S. And they might say, well, what about that other 2 upstairs? We've got to deal with it, but we have ways. So let's first work on rewriting it. Okay, so this is, we'll say the inverse Laplace, and the first part will be e minus s, 1 over s minus 1. And then we're going to subtract e to the 2 minus 2s. Now, we're going to use properties of exponential functions. Right now we use properties of breaking up upstairs. It's easy to do. If you have e to the power 2 minus 2s, we can separate that into 2 parts. So that's going to be e squared e minus 2s. Okay, so that's our e to the 2 minus 2s, e squared e to the minus 2s. And then we still have a 1 over s minus 1. Why did we do that? Well, because we really don't have a rule for this, but we have a rule for e to the minus 2s. And what is e squared? It's constant. And we can handle constants. We have ways. And what are our ways? We just pull them out. And so we really could actually write this as inverse Laplace of e to the minus s, 1 over s minus 1, minus e squared, inverse Laplace, e to minus 2s, 1 over s minus 1. Okay, now we're ready. All right, good. So, anticipating, we'll write down another rule, because who doesn't like to write down lots of their Laplace transform rules? E to the ct, 1 over s minus c. Okay, so what do we have? Well, this e to the minus s is telling us we're going to have a shift. So that's u t minus 1. Now, 1 over s minus 1, what is that? Now, normally, 1 over s minus 1, if we apply this rule, this would be e to the t, just by itself. And we say, okay, well, if it's e to the t, now it's going to be what? Well, it's going to be e to the t minus 1. I'll put parentheses here. They're not needed, but I just want to emphasize that's what's happening. E squared is a constant. And now this e minus 2s says, again, shift. So, okay, so that's going to become our u t minus 2. And we still have that 1 over s minus 1 hasn't changed in the last 30 seconds. Still e to the t. So, okay, but we need to do it as e to the t minus 2. Right? Good. And so, what do we have? Well, we can do one more cleanup here. So we have u t minus 1, e to the t minus 1, and notice we can combine. So this e to the 2 can combine, so it's t minus 2 plus 2, which will leave us with u, u t minus 2 e to the t. And there we go. So ultimately this 2, e to the 2, ended up coming in. And, well, we couldn't tell that at the start. Well, that's all right. You do the process. And the process is helpful, right? All right, good. Well, more practice. Let's do a few more problems. So let's find the inverse Laplace 6s minus 9 e to the minus 2s over s minus 2 s plus 1. Cool. What's our tool that we're going to be using here, right? Partial fractions, right? It feels like partial fractions. Are we ready to do partial fractions right now? No. Okay, so I want you to be careful. And because I don't want you to make mistakes, I want you to get it right. And this is a mistake I've seen other people make, but of course, you're the good student. You're practicing, you're doing the work. So I believe in you. So let me just point out something here. When we're doing partial fractions, when can we do partial fractions? So for partial fractions, we need polynomial over polynomial. It has to look like that. If it's not polynomial over polynomial, partial fractions doesn't work. It breaks down. Now, what's our problem? Well, we definitely have polynomial downstairs. Our problem is this e to the minus 2s upstairs. That's not polynomial. So, what do? Well, we're still going to do partial fractions, but the thing is we want to make sure that the exponential piece is not involved in the process. So how do we get to that? Well, what we do is we say, let's pull things apart upstairs so that we can put the exponential piece off to a side. So let's start by rewriting our problem. So this is our inverse Laplace of 6s over s minus 2 times s plus 1, and then minus 9 s minus 2 s plus 1 e to the minus 2s. So, did you see what happened here? We used our subtraction sign upstairs to help split into two parts. And then we said the first part, that's fine. The second part has an exponential, and we kind of nudged it off to the side. And now we say, cool, what can we do? Well, what we can do is we say, hey, we now have two pieces, and for each piece, we're good to go. So that means we don't get to do one partial fraction problem, we get to do two. Nice! Twice the work. Ah, Wonderful. Well, that might not be your initial reaction, but let's go ahead and do it. Okay, so we'll start with the first one. 6s over s minus 2 times s plus 1. Well, okay, we see our pieces downstairs, so we know we want something over s minus 2, something over s plus 1. Well, we'll call these a and b. We're going to clear out our denominators. All right, and when we do that, we're going to get 6 times s is a s plus 1 plus b s minus 2. And I like to make good choices. I think that's a great way to approach math, great way to approach life. So let's make some good choices. Suppose we choose s equals 2. Then we'll get 6 times 2 is 12, equals a times 3, 3a, and b times 0. So say, oh, that says a is 4. All right, how about another good choice? -1. Now if you're wondering, like, where are these good choices coming from? We're trying to make stuff 0. 0 is a wonderful ally. So -6, a times 0, and then -1 minus 2 is -3. So -6 equals -3b. So that says b is 2. All right. Now, what does that tell us? Well, it tells us that we're going to update, and so we're going to say, as this says, the Laplace inverse, the 6s over s minus 2 s plus 1 is going to become 4 over s minus 2, because that's our a, and then we're going to have plus 2 over s plus 1. Okay, so I've broken that apart. Okay, but we left ourselves room because we're going to write more. That's all right, no worries. Now, the next part, this part. So 9 over s minus 2 s plus 1. Well, that's going to be something over s minus 2, something over s plus 1. Yeah, we'll keep working our way up through the alphabet, C and D. Again, clear your denominators. It's going to feel very similar to what we just did, because it is very similar to what we just did, right? And so, because it's similar, it'll help us. It tells us what to do. We're going to make good choices. In fact, we're going to make the same good choices. So plug in 2. 9 is equal to c times 2 plus 1. So 3c, and then 0. So that says, oh, c is 3. And plug in -1. And then we're going to get 9, well, because there's no s on that side. All right, 9 is equal to, here we go, c times 0, and then minus 3 times d, minus 3d. So, okay, d is -3. All right, great. So, now what's going to happen is we're going to subtract, and then I'm going to be careful here. So I'm going to put parentheses just so I don't lose anything. 3 over s minus 2, and then -3 over s plus 1. That's e to the minus 2s. All right, so we did our partial fractions, but we were very careful to make sure we have polynomial over polynomial so that everything worked out correctly. Let's do a little bit more of rewriting here, because who doesn't like to rewrite stuff? I think if there's one thing that you need to remember, the majority of the work here is rewriting to get to the point where it's like, aha, my table now works. And then doing the table part is pretty quick. Doing the writing part is like, all right, and then we do this. So I hope you like to rewrite stuff. On the first part, we're going to think of this as 4, 1 over s minus 2, plus 2, 1 over s minus 1. Okay, distribute through, we'll have a minus, we'll put 3 e to the minus 2s, 1 over s minus 2. Minus minus makes a plus, so plus 3 e to the minus 2s, and then 1 over s minus minus 1. Whew. Okay, now we're ready. Here we go. So, term by term. That's how we do problems, right? Piece by piece. And what are we going to get? We're going to get the following. 4. 1 over s minus 2 is e to the 2t. Plus 2. 1 over s minus minus 1, e to the minus t. All right. Then minus 3. E to the minus 2s. Now that tells us we're going to have a shift by 2. So u of t minus 2. Now this part, 1 over s minus 2, we know what it is. This should be e to the 2t. So it's going to become e to the 2, and then it's not t, it's t minus 2. All right, and then our last part is plus 3, and again, e to the minus 2s, u of t minus 2, and then we're going to have here, this piece we've already done, that's e to the minus t, so it's e to the minus t minus 2. And we're done. Now we could do various things. We could certainly put those together, but at this stage there's not really much that in the way of simplifying into collapsing a lot, and so there you go. There you go. Well, you know, no big surprises. Just make sure to be careful, and so that things work out nicely. But that's not a surprise. That's what we've been doing all along. All right, I think we have energy and time for one more. So let's do one more. So for our final problem, the inverse Laplace, upstairs 3s minus 11, e to the 12 minus 3s, downstairs s minus 4 squared. And we're told, simplify your answer as much as possible. Now, when you see something that says simplify as much as possible, it probably is going to be really simple. And so we are strongly anticipating a simple answer. So if we get a complex answer at the end, we're going to start to question ourselves. But before we do that, let's not question ourselves. First, let's wait till the end and let's get going. Okay, so what can we do? Well, let's first think about this 3s minus 11 over s minus 4 squared. Now we could do this by partial fractions, but since we just did some partial fractions work, I'll point out something here. When you have, s minus a squared, you could say, well, can you make the top look like s minus a? So in this case, could you make the top look like s minus 4? Well, we can try. So that's not an s minus 4, so I'll make it an s minus 4. That was pretty quick. But now, does 3s minus 4 match with 3s minus 11? No, it's not quite right. Because what happens? You get 3s minus 12, not 3s minus 11. Oh, well, add 1. Oh, sounds good. And so this becomes 3s minus 4 over s minus 4 squared plus 1 over s minus 4 squared. Or, if you like, that's 3 over s minus 4 plus 1 over s minus 4 squared. All right, so that's sort of partial fractions. There's oftentimes lots of ways. So just partial fractions is one tool. If you see something, you're allowed to do something. But if you don't see something, you always have the tool to fall back on. All right, so let's see where we're at. We want the inverse Laplace of, well, we have our pieces here, our 3 over s minus 4 plus 1 over s minus 4 squared. Now, this e to the 12 minus 3s, we're going to do something similar to a previous problem, which says we don't want this 12. We just want e to the minus something s. So we say, well, that's e to the 12, e to the minus 3s. Okay, so we're just breaking up that exponential. into two pieces. Now, e to the 12 is a constant, so it can pull out to the front. So we say, all right, this is looking pretty good. So we have e to the 12 inverse Laplace of, then we have our, well, maybe I'll put the e to the minus 3s up front. It doesn't matter as long as you keep track of it being there. Then 3, 1 over s minus 4. And then here, plus 1 over s minus 4 squared. All right, so we're ready to get into it. Now, piece by piece, what's going to happen? Well, with this e to the 12, we're going to get e to the 12. It's a constant. Oh, well, okay, that's great. Cool. This e to the minus 3s tells us we're going to have a shift. There's this on-off u of t minus a. So we're going to have a u of t minus 3. Okay. Now, we look at this expression here, and we ask ourselves, what's going on? Now, there's a couple of things coming into play here, so don't rush it. So if we weren't worried about this part for right now, we'd say, well, this would be a 3, this would be an e to the 4t. Now this part right here, if you weren't worried about the 4, right, you just saw 1 over s squared, you'd say, well, that should be a t, right? You'd be right, it is a t. So it would be a t, and then you say, but aha, you are worried about that minus 4, and that comes from another rule says you'd add an e to the 4t. So an e to the 4t is accounting for the shift in s. Okay, so the shift in s, that's the e to the 4t. And now we say, all right, because we see this e to the minus 3s, we're going to take this whole expression, and everywhere where we see a t becomes t minus 3. So we have 3 e to the 4 t minus 3 plus t minus 3 e to the 4 t minus 3. All right? So it's kind of interesting here. You have to keep track of your rules because you have this minus 4 down here, this s minus 4 introduces this e to the 4t, and this e to the minus 3s says, okay, all of these t's become t minus 3s. So be careful here. Work through your layers. These problems, they're onion problems. You've got layers. Just take your time, one layer at a time, and like onions, tears may be involved. Hopefully, tears of joy. Now, what can we do? Well, since we see e to the 4t minus 3, that's common, pull it out. Why not? Let's make it look pretty, because our goal is to simplify, so we should try to make things look pretty. So we have e to the 12, e to the, and they're both have 4 times t minus 3, so we'll write that as 4t minus 12. So we've pulled the exponents out. We have that u of t minus 3, and when we have pulled it out, we've had 3 plus t minus 3. Now, what happens? Well, e to the 12, e to the 4t minus 12, put the exponents back together, and you get e to the 4t. 3 plus t minus 3 becomes t. Let's put that in the front. U of t minus 3, u of t minus 3. And that is very simple. We're not going to be able to hope for anything simpler than that. Beautiful. Good. Good. We got there. We got there. And we got there by following the rules, taking our times, not panicking. We are calm. We're doing math. We're in our happy place. And so thank you for joining me in my happy place, and I hope you'll join me again. Bye.